Figure 2 shows a sketch of the graph with the equation y equals 2 times the modulus of x plus 4 minus 5. The vertex of the graph is at point P, shown in figure 2, and we're asked to find the coordinates. So this is essentially a critical point of the modulus function. It's where it changes, well, from the modulus function from not doing anything when the whatever's inside is positive to when it does do something when the inside is negative. And the critical point is when the inside becomes 0. So it's going to be when x is minus 4. And then normally it would just bounce off the axes here, but because we've got a minus 5, it's actually translated it in the negative y direction. So we're actually going to get minus 4 minus 5 as point P. We're then asked to solve the equation 3x plus 40 equals this function. Now, I think a little sketch of 3x plus 40 is a good idea. I always use sketching to solve modulus equations. It just gives a bit of insight into what's going on. So there's a steeper gradient, first of all, and the y-intercept is going to be at minus 40 over 3. It's going to, I don't know, it's going to be sort of be something like this. What we can see is it's not actually going to intersect with this part of the modulus curve because of the steeper gradient. It's definitely going to intersect the kind of the negative part. And so all we have to do is do 3x plus 40 equals, and then kick in the modulus part. It's going to be 2 times minus x minus 4, then minus 5. This becomes minus 2x minus 8 minus 5, that's minus 13. And then 5x is going to equal minus 13 minus 40, that's minus 53. And if you do 53 divided by 5, you get minus 10.6. That is the only solution to this equation. And like I said, you don't need to actually solve for the positive one. In fact, if you do, you'll get a spurious solution. I think I'll just show you what would happen. So we do 3x plus 40 equals 2x plus 8 minus 5. However, we must recognize that x has to be greater than minus 4 for this to be true, because we're past the critical point to the right. Then I'd get x is equal to, well, this would be 3 minus 40, x would equal minus 37. And we can see that this doesn't work. It would actually be what would happen if we carried it on down here. Eventually they would meet again, but it's not actually a solution to our problem. In the final part, we're told that a line has equation y equals ax, where a is a constant, and we're given that this line intersects the modulus function at least once. Find the range of possible values of a, writing our answer in set notation. So this line necessarily goes through the origin. Therefore, I'd get 2 points of intersection there. I could even have a negative gradient. I'd get 2 there. So I'm kind of interested in the boundary where I don't get any solutions, in fact. And one way that I just get one solution would be if it just clipped that very bottom vertex like this. So if the gradient is going to be less than that, I'll go through twice. But if it's equal to that, it'll just hit it once. That will actually include it intersecting, but if the gradient is then slightly more, it would end up looking like that, and it wouldn't have any. So let's find out that gradient. That's going to be on the threshold, essentially. So remember, this point P is minus 4, minus 5, which means that I'm going to be going along 4 and up 5 to get to the origin. So if A equals 5 over 4, line will just touch vertex. So if A is less than or equal to 5 over 4, there will be at least 1 point of intersection. Normally 2, but in a special case 5 over 4, just 1. Let me just demonstrate that. So if we go 5 over 4, that's just when it hits it once. If we go beyond that, we're going to get it going through twice like this. Yeah, still twice here. Even when it's the gradient 0, goes through twice. Again, as it continues to get more and more negative, it's just coming around. Now, at some point, that's still going to intersect twice. At some point, it's going to be parallel to that one on the left, and it's just going to go through once. But still is a point of intersection, so it doesn't matter how negative you make the gradient, how big, it's going to go through that right-hand one. So what happens? Are there any values above 5/4 where we're going to get points of intersection? The answer is yes, because let me do this in green. So if I make it really steep and positive, you can see that it's going to go through once there. So there's got to be a cutoff kind of for the positive side as well. And it's going to be, and I kind of hinted at it with the one on the left when it was parallel to this curve on the left. What if we make it parallel to the modulus function part on the right, like that? That will not get any points of intersection. And actually, any line in between 5/4 and that won't either. So if I just kind of squeeze another line in there, no point of intersection. And that green line corresponds with a gradient that's parallel to the modulus one. So it's going to be 2, because it's 2x plus 4. When the function's positive, we just get 2x plus 8 minus 5, so 2x plus 3. The gradient's going to be 2. So we require the a to be bigger than 2 as an alternative. So if a greater than 2, line will also intersect. So in fact, it's the region between 5/4, not inclusive, and 2, inclusive, that's going to mean there's no points of intersection. Otherwise, we've always got at least 1 point. And therefore, for our set, it's going to be the set of A such that A is less than or equal to 5/4. Definitely includes that point as well. Sorry, not intersected, unioned with the set of A such that A greater than 2. All of those possible values of A will lead to at least 1 point of intersection. I think it's crucial to practice the graphs. This is a bit of an unseen question. I have seen stuff like this on Edexcel, so it's all about just trying to draw some lines, figure out what's going on, and finding these thresholds and realizing in between there's no solutions, but outside of the range there are two. Well done.